Okay, so I sent you all earlier an email with a new exercise. So hopefully you've had a moment to already start that process on your side. If you have not, then please make sure to do that. We're going to start covering some of the some explanation initially of the algorithm that we're going to learn today. And so you're going to have some time to catch up if you need to. But in any case, go ahead and follow the instructions on that email to get you started on the project for today. If you were already able to do all that, then make sure you go ahead and launch your RStudio project for this new exercise 12 PIT. So let's go ahead and launch that. And again, always you want to make sure you are in the right project. Go ahead and launch the partial script if you have not done so yet. And then we're going to get started. Okay, so today our learning objectives for this exercise are going to be to understand a new algorithm. This algorithm is called conditional inference tree, or CIT for short. We're going to again use the same machine learning workflow that we learned on the previous class to pre-process the data, train the model, and evaluate the model predictability. And today specifically, I want to introduce a couple of new concepts that we did not do last time. We could have, but I wanted to, start simpler and then build from there. So today, the two new concepts that we're going to implement, one is going to be to change our grid or the hyperparameter fine-tuning search. Last class, we used a fixed grid. Today, we're going to do one iterative search method called simulated annealing. So that's going to be a new topic for today. And again, we could have done this on the previous class as well. We could do a fixed grid today here as well. There are two different methods as we saw in lecture, and you can choose whichever one you want. It's more that today we're adding one level of complexity to that part of the training process. And also today we're going to be doing something new that could have also been done last time, but I'm introducing today, which is, if you remember last class, we selected the best model based on whatever model gave us either the highest R square or the lowest RMSE. Today, we're not going to simply select the best. We're going to select the best within one standard deviation. Because sometimes, maybe your best, let me just make up some numbers here. Maybe your best model has a test set R square of 0.8. And then your second best is 0.79. Are those really different? Maybe not. And maybe your second model that has just a very slightly lower R square may be a simpler model that would be easier to port or to even interpret. So the goal here today is, instead of selecting just the best model, let's say based on highest R square, we're going to select the best within one standard deviation of R square among the different models that are being created from different hyperparameters. So that's going to be another difference from the previous class. All right, so I think before we start talking about this algorithm, I just wanted to check in with you all and see if anyone has any questions, maybe about, the workflow in general, or maybe from last class, if you have something that you would like to ask before we start with the new algorithm altogether.
Dr. Vestas,
Yes, right here.
what is porting a model?
So porting a model would basically be, if you create, so we're training these models here with the intention that you can make predictions, right? So maybe let's say if you want to deploy your model on a dashboard, like if you want to allow people, now that you train your model, you want to make it available for others to upload their data and get a prediction, that would be porting a model. That would basically be you deploying, perhaps is the best word, your model.
Thank you.
Yeah. All right, so let's get started with today's algorithm. So we already saw on our multivariate class that multicollinearity can be a very important issue, especially with linear models. And that happens when two or more of your predictor variables, of your X variables, are highly correlated. We also talked about some ways to remedy this. So one of them would be to run a principal component analysis, for example, to do dimensionality reduction. And if you remember, PCA does not only do dimensionality reduction, it does in a way that the new principal components are orthogonal, or in other words, independent, or in other words, non-correlated. That is something very specific about PCA. And then we can do also in or variable selection, right? We talked about doing variable selection by hand, which is basically you using your expertise in your fields to only provide a model with variables that do make sense and not just throw everything at it and hoping that the model finds for you things that perhaps don't make sense. And the variable selection can also be done by the models themselves, right? So last class, we talked about ElasticNet, a model that does variable selection using two different types of penalties. So that is one of the ways that at least that model does variable selection for us. In this case here, our model of today, conditional inference tree, also does variable selection, although in a different way. And we're going to see that how that works in a second here. So this algorithm, or this general algorithm called conditional inference tree, is a recursive model that works in iterations, and in each iteration it performs two steps. The first step is going to be to select a variable that is related to so selecting a predictor variable in relation to your predicted variable. And once it selects that variable, it does a binary split of your data based on that variable. I know this sounds very vague now, but we're going to go through some examples that will help you understand what I mean by that. But basically, just keep in mind that these two steps of selecting a predictor variable and doing a split on that predictor variable happen multiple times within this algorithm in a recursive way. The way that it performs variable selection is first, it basically runs. So imagine that on our models, we're explaining strength by all these 72 other variables. On the first iteration of this algorithm is basically going to do strength explained by each one individual of our predictor variables, and then select whichever one gives the lowest p-value of that bivariate relationship. So imagine, for example, strength explained by mean July solar radiation. Then strength explained by mean August solar radiation, and so on. It does that individually, those bivariate relationships individually with all of your predictor variables. Whichever one creates the lowest p-value, that's the predictor variable that it chooses. It chooses that variable. So let's say it chose solar radiation in July as the one that had the lowest p-value when explaining the strength. It chooses that predictor variable, solar radiation in July, and then it looks for a breakpoint of this. Imagine strength and solar radiation, and you have this scatter plot. Once it selects that predictor variable, it's going to search for where on this x-axis of solar radiation can it break the data in a way that minimizes the error on both sides. It's going to search for that breakpoint on the predictor variable, make that breakpoint, and once it finds the one that minimizes the error of both broken parts of the plot, and then it makes a split based on that breakpoint. Now that makes a split, let's say it says, it finds a breakpoint of your predictor variable. So it's going to say, well, if solar radiation in July was greater than whatever value, let's just make like X, call that X, then you go to the right. If it was lower than the value, you go to the left. Now you have two new subsets of your data in each one of these paths that you took. And now on each one of those subsets, it redo the same recursive steps. For each one of those new subsets of your data is going to rerun again strength by all of your variables. However, now just at that subset, look for the one with the lowest p-value, find the breakpoint, and potentially break again. We're going to see a plot of this that I think is going to help you understand. But basically, that's what's going on with this algorithm. And then if you imagine this tree could grow indefinitely until you basically have one observation per terminal node. Although I think I'm going to keep this explanation to a little bit later so you can see what I mean by terminal node. But the key point I'm trying to say is this tree can be very, very, very complex, which is probably an issue for overfitting. So we need to find a way to allow this tree to grow just enough, but not excessively enough. We don't want it to overfit. So if you remember the bias variance trade-off, this is a model that's very easy to allow it to be too complex. And we want to make sure it is complex enough, but not more complex than needed. So we're going to have some hyperparameters that we're going to choose to help us basically not allow this tree to continuously grow forever. So we do want to have a way of stopping it from growing. So one of the stopping criteria, for example, would be the maximum tree depth, which is how many layers that tree is going to have. We're going to look at one example right now. So this, I think I pulled this from a paper. It's not one of my papers, although I do use a lot this analysis. Let me see if I can actually go to this URL to show you, because it looks kind of small in our. Oh. Yes, Ashbin.
Dr. Bastos,
Yes, go
can
ahead.
you hear me?
Yes.
Okay. How the CIT is like different from the conventional like traditional decision trees?
So this is one type of decision tree. There are different types of decision trees, and the main difference is basically, well, there could be a couple of different differences, but one of them is maybe the way that the tree selects variables may be different. So one example is the algorithm that we're going to be looking into, the metric that the algorithm uses to select a variable at each step is the p-value. Other trees may have a different metric. So other trees may use R² as the metric, which will give you a different tree for the same data set. Perhaps the difference may be on how the tree finds the breakpoints of the predictor variables. That could also be one difference there. So overall, this is one type of decision tree, and it's specifically called conditional inference tree. All right, so let's look into this example here. What is going on here, and let's talk about this terminology. So basically, the way that we would read this output of this analysis, you would basically start from the top. So starting on the top is where you have all observations of this data set, or at least the data set that was given to the model. Starting on the top, you have all of them. So on the first step on this algorithm, it basically ran, again, in this example is explaining grain yield as a function of a lot of different variables. We see that the first variable that the algorithm selected was cumulative rain with a p-value of less than 0.01. So it first selects that variable. So basically at that step, it had all the data points, all the rows of this data frame. It did grain yield by each one of the variables, of the predictor variables, and it found that the relationship of grain yield and cumulative rain had the lowest p-value. So it selects cumulative rain as the most important variable at that point. Once it does that, imagine that you have this scatter plot of grain yield by cumulative rain, and then on the axis of cumulative rain is going to try to put a vertical bar as a breakpoint on cumulative rain in a way that whatever level of cumulative rain that it makes the breakpoint, it is minimizing the error of both sides of what's left on grain yield. So basically here, the breakpoint that it found was about 388 millimeters of cumulative rain. So if you have less than that, or at least for this data set, you would go to the left here. And then there is a subset of your data. So let's say here they're not showing n at each one of the nodes, but let's just make something up here. Let's say that n, or node total number of observations on the top, was 1,000 observations. Then whichever number of those 1,000 observations have a cumulative rain of less than 388, let's say that that was 300 observations. Those 300 observations would come to the left, and then now you have a subset of the data, just 300 observations, but then it does again with only those 300 observations, grain yield by all the variables. And in this case, you found that PAWS, but you don't remember what that stands for. But it's probably a water-related variable. Potential, or I don't know. I'm not going to try to guess. But whatever variable this is, it found that that variable was then the most important for this subset of the 300 observations that had a rank cumulative less than 387. And then it does again the partition here, and it found that based on this PAWS variable, if it's less than 184 millimeters, you go to the left. If it's more than 184, it goes to the right. And then you have finally your terminal nodes, which is where the actual predicted variable, in this case, grain yield, is going to be found. So for example, we're going to see here, if we take cumulative rain and go to the right instead, we would see if we have cumulative rain more than 388 millimeters, then the next important variable is going to be the flag leaf fungi, which notice now it's a categorical variable. It's yes or no. So this is yes or no. This is a character, right? It is a categorical variable, which is one thing that conditional inference trees do, is that they can, both the predictors can be numerical or categorical. Also, the predicted variable, the y variable, can be numerical or categorical. In this case here, the predicted variable is grain yield. It is numerical, but this algorithm handles both types. So anyways, if we come here, cumulative rain, more than 388, it goes to the right. The next most important variable is flag leaf fungi, yes or no, and then it keeps trickling down. Now, one thing to notice here is if we are trying to understand what are the main drivers of grain yield with this algorithm, we would come on the terminal nodes, which is where basically the tree stops growing and you have these box plots. And we look at grain yield, we can really see that the highest grain yield was observed on this terminal node. So the way that you would interpret this is, how did you get to this terminal node? What were the variables and what were the conditions of those variables that get you the highest yield? If you just trace that back, it would basically be cumulative rain more than 388 millimeters, flag leaf fungi, yes, and then first nitrogen rate more than 87 kilos per hectare. That gives you the highest yield of this data set. That's how we would interpret it. Similarly, you could look into the lowest yield, which is on this terminal node. The condition for the lowest yield here would basically be cumulative rain less than 388 and PAWS less than 184. So as you can see, there are different conditions that generate a gradient of terminal nodes in this case. Let me return to the script because I think there's some important points there that I want to make in the order that I have there. All right, so 3 terminology concepts for this algorithm. The root node is basically the one on top. That's the one that has all the data rows. And something I want you to imagine is, imagine you have, again, 1,000 rows in this data frame. Each time you do a split, there's only a part of the data set that goes to each side, right? It's not like you have 1,000 rows everywhere. Like you start with 1,000 and then that starts being split into subsets of your data. So each split here is representing a subset of your data. That is the subset matching the condition at that level. So root node is the one on top, the one that has all the data rows to begin with. And then we have the internal nodes, which are all the nodes in between the root node and the box plots. So everything in between is an internal node. And then we have our leaf or terminal node, which are the ones at the bottom here that really show you the distribution of a predicted variable according to the model above. Really, the most important to remember is the terminal node, because that's what you're going to really look into to understand how your predictive variable was impacted. Another feature of this algorithm is that variables that appear first when you're reading from the top to the bottom, so variables on the top are most important. They have a greater importance than variables that come after them. So it also gives you that variable selection through that process. And again, now that I said the word variable selection, I want to just go back to a concept that the reason why this algorithm is not prone to multicollinearity is because even though it is a multivariate analysis, it is only doing variable selection on a bivariate relationship. So it runs all bivariate relationships at each step. It never runs a multivariate model in that sense of like strength explained by all these variables. It's just strength explained by each individual variable separately, choosing the one with the lowest p-value, and then doing binary splits. That's how this algorithm handles, or that's how it remedies multicollinearity. So even though the ensemble of it is a multivariate model, but the individual pieces of that tree are all derived from a bivariate relationship. All right, I guess any questions about what I just said? Yes.
Too many internal nodes can be a bad thing or a good thing?
Yes. So Priscilla is asking if having too many internal nodes can be a good or a bad thing. We're going to talk about that next, but really the key is that then the reason why these models have to be really trained is because, so let me just go back to the plot that I had here on the browser. It's this one. Okay, so here you can see that at least on the terminal nodes, at least on this plot, you can see it tells you n. So basically this box plot here is made out of 61 observations, and then 86 and 82 and so on. If you imagine the extreme of overfitting with this model would be each terminal node being one observation. That's the extreme, and that we never want to do that, right? We don't want a model that can predict an observation specifically, because then it's definitely overfitting, right? You're touching that observation on, if you think of that plot that we saw. So that's definitely what we don't want. So the two extremes here, one extreme is, so the very overfitting extreme is each terminal node is at one observation. The other side of it, the oversimplified, is there are just no splits. It's just one data just by itself, which could happen sometimes. I've seen that a lot of times where maybe you don't have enough data, or maybe your predictors are not really strong, and depending on your hyperparameter values. So let's say, well, let me not get too complex quite yet, but just think of the two extremes being no partitions at all, or all partitions possible in the way that your terminal nodes, each one of them is one observation. Those are the two extremes. Now we're going to train the model to be somewhere in between, right? So yeah, having a lot of internal nodes can be bad if you're overfitting, and we're trying to avoid that. All right, any other questions? All right, so let's keep moving here. So let's understand how it is creating partitions. I'm going to use yet another example, not from our data, but it's a very simplified example that will help you hopefully understand how these partitions are happening. So in this example, I'm going to show you, we basically have our predicted variable, a y variable, and just one predictor variable. So it's just a y explained by x, 1x. Very simple, just for us to create the understanding of what's going on behind the scenes. So this is another representation of a conditional inference tree where we have our variable on top. Our y variable is being explained. I mean, we don't even have to, it doesn't even have a name. It's just y by x. So just keep those terms in mind. So basically it found that when explaining y, if the x variable is more than 3.1, it goes to the right. And if it's less, it goes to the left. And then you see that in this case, it's basically partitioning the data. 51% is coming to the left, 49% is coming to the right. if we were to make a scatter plot of y by x, and then remember, in this case, there's only one x, so it's not really doing variable selection, it's just doing variable partitioning in this case, in this very simple case for us to understand. So if we were to make a plot of y and x and show exactly where that split is happening, this is what you would see. So x variable on the x-axis, y on the y-axis. It found that this single split to be an x value of 3.1. So this is the vertical bars kind of splitting that data. So the way that it found that partition, so it tries many partitions on the x variable, and there's just one solution here that is going to minimize the error of both what's on the left and what's on the right. That's the value that it does the partition. So what we're seeing here is, so we have this scatter plot. The blue line is what would be the true relationship of x explaining y. And then the red line is basically what the partitions are creating. So all the points that are lower than this vertical red line would go to the left. All the points to the right of it would go to the right on this representation of the tree. That's what's going on. Now we can allow this model to be more complex. As we saw, if we just make this and then basically the terminal node, although here is not showing that way, but the terminal node would be a box plot with all these points on the left, all these points on the right. So imagine two terminal nodes with two box plots in this case for all those points. As we can see, this tree that we just saw is perhaps too simplistic, right? It's underfitting our model. It has like just two groups. Maybe we could have a few more groups to better, I guess, better match the truth blue line here. Now we can allow this tree to be deeper. So in this case here, again, there's only one x variable, but as you can see on each one of the internal nodes is basically finding new breakpoints within that x variable at each one of these partitions and just making more partitions based on x only. And then in this case here, we end up with having a lot more terminal nodes in the end. If we were to go back to our y by x scatter plot and see where these breaks happen and how is that further breaking down the data, it will look like this. So every place you have like a vertical step here, that would be, if you were to project that on the x-axis, that would be the threshold that you're seeing in one of the nodes of the tree. As you can see now, we are breaking that red line more times because we're allowing for more terminal nodes and therefore better matching the shape of this blue line. And again, at each one of these breakpoints, all the points that are within, so let's say within two breakpoints, right? So here's a breakpoint, here's a breakpoint. All these points here will show up as a box plot on the terminal node if you're showing as box plots, as in the first example. And that is very common to show as box plots when your predicted variable is numerical, like ours is. Now, I guess going back to perhaps answering your question, Priscilla, this can become very complex. So imagine if you just allow this tree to grow to like a very complex tree and having many terminal nodes here. Now, if you were to make that same plot and identify each one of the breakpoints of each of the internal nodes, it will look like this. So very complex. You're ending up. So another way of thinking of this is because you're partitioning your data at each breakpoint that you make, if you have too many breakpoints, you're going to have fewer observations in the terminal nodes, right? Which I guess is what I guess we cannot really see here, but if we were able to really see the numbers on those terminal nodes, you would see that would have very few observations in each one of the terminal nodes. And then this is how we would approximate that blue line. This to me looks overfit, right? Like it looks like it's fitting noise already. We want to fit the actual shape, but not noise. Something to also notice about conditional inference trees is that the prediction is never going to be smooth, because what happens here let me go back to our first example that is more understandable, perhaps. What happens here is whatever grain yield data point that matches all those predictor variable conditions, all of those yield points, although we see a variability of the yield points that got to that terminal node, but if you were to make a prediction based on this model, the prediction would be the mean of that terminal node, regardless if the yield was higher or lower. As long as the predictor variables match that pattern, the prediction the model is going to give you is the mean of that terminal node. So it's always going to give you the same prediction, even if your predictor variables are slightly changing, but still matching the same internal conditions. We're going to see this in our when we apply to our data. So I just wanted to bring that up for you to be aware, but we will be able to see that in our data, applied to our data. All right. So yes.
I guess I'm kind of bouncing off Priscilla's question a little bit, but how do you know when it's overfit or underfit? Like, do you just have to visualize it like this, or what's in game? Because at each tree, you say, oh, this is slightly, you know what I'm saying? So
Yeah.
what's in game? Is it just a visualization that determines when it's overfit or underfit?
So, okay, so let me just repeat that for those online. So Jonathan is asking, how do we objectively know when it's over or underfitting? Like, we can visualize, but how can we actually put a number on it to say over, under, or good? So every time that we're trained, so the reason why we train models, and the word train here comes back to the fact that we're doing data splits, finding the best hyperparameter values, and then creating a model from that. That training process is one of the ways that we're trying to optimize the selection of hyperparameters that optimize this tree, or optimize any algorithm, right? So if it all comes back to that concept of, if you remember, we had the plot that when we're talking about the bias variance trade-off, that if you keep increasing model complexity, your training error will always decrease, your test error will decrease, and then if you make it too complex, it will increase again, because now the complex model is modeling noise. So it's like remembering the training data, but it's not general enough to make good predictions on unseen data. So basically we use those metrics. So the fact that we do data split and spend the data in different ways in the training process. And one of the ways we're spending is to find the best combination of hyperparameter values. And then once we get to those values and we have our final model, we predict that on our test sets, which the model has not seen. All those things are making sure that we are doing our best to create a model that is not over or underfitting. Yeah, so that's basically every time people talk about like machine learning and training models, we're always thinking of, okay, the goal here most of the time is prediction. And so if that is the case, we want to make sure that we do the proper training methodology in a way that the final model is not overfitting or underfitting, is the best model possible given the data we have. We're always going to make some plots like this as well, so you can like visually assess subjectively perhaps, but it's going to also be relying on those concepts. All right, so how can we control how simple or complex this tree is going to be? Well, we're going to fine-tune our models and do so in a way that we're spending our data the best way possible. So again, one thing I would like for you to get out of this course, perhaps, especially the machine learning side, is we're going to be talking about 4, maybe 5 machine learning models in this class, but there are many more out there. So my goal is for you to understand how we're going about this process in a way that you can implement it on your side when you're trying to learn something new that uses this process. So one of the goals here is to first understand how the model works, right? How is it working behind the scenes? And then understand what are the hyperparameters that has available for you to control model simplicity or complexity. Conditional inference trees have many hyperparameters that we could use to control complexity. What we're going to be using or training is going to be two of them in this class. The first one is called maximum depth. So this would be how many, well, I just saw that I have the wrong word here. So not vertical, but the maximum, well, let me think about it. No, it is right. Sorry. So the maximum depth of the tree. So if we go back to the tree, or even these examples here. So this tree has basically one depth, or it's one layer deep. Whereas this tree is 1, 2, 3 layers deep. This one, I don't even know how many, but if you were to count how many layers you have, how many horizontal layers stacked on top of each other, that is one of the things that we can control in this tree. So we can say, well, I just want a tree that has 3 layers. So it's not going to grow more than having 3 layers in this tree. That is one of the ways we can control complexity. The other way we can control complexity is by changing the minimum criterion. So this value is a value of 1 minus p-value that must be exceeded in order to implement a split. So when is the case that maybe you have no splits in your tree? This would be perhaps, so if you think of like, so maybe your minimum criterion would be, if we use a threshold, a p-value threshold of 0.05. So your 1 minus 0.05 is going to be 0.95. That's your minimum criterion. If there is no bivariate relationship between your predictive variable and any of your individual predictor variables, so let's say you do all those bivariate relationships, all those scatter plots, all those correlations, and then the p-value of all of those is from 0.1 and above. So from 0.1 to 0.9, let's say. There's nothing that's highly significant. Your tree is just not going to split because it did not find a significant enough relationship between your predictive variable and any individual predictor variable to then even just start doing variable selection and splitting. So the minimum criterion here is, again, think of it as the p-value that you're requiring the tree to find a relationship between your predicted and predictors to be able to then select one and do a split. If you make this, so if the minimum, well, maybe if you think of the p-value is a little bit easier to think of it. But imagine that you said, well, my maximum depth is going to be 10, and my minimum criteria, or my p-value to do a selection and then split is going to be 0.00001. You're being very restrictive on your p-value. Maybe none of your variables have that low of a p-value in a relationship between x and y, and therefore no splits will be done. Now, if you're very liberal, you may say, well, I want to do a p-value of 0.1. Now, maybe you have many splits on this variable, on this tree, because a lot of your variables have that relationship that is at least a p-value of 0.1 between y and x. So here is how much liberal or how much you're restricting the significance between the relationship of x and y for it to even start selecting a variable and doing variable selection. So those are the basically the two ways that we're gonna control how complex this tree is and use that in the training process. All right, let's talk about some pros and cons of this specific model. Some of the pros is that is non-parametric. What I mean by that is it does not assume a specific distribution of your data. It does not have any assumptions of, let's say, residual normality, for example, or even data normality for that matter. So it's non-parametric, is not assuming any specific distribution of your data. It is very, it's one of the good things about it is that it can model nonlinear relationships. As if we go back to our previous example here, the blue line, which is the truth, I mean, I think you could perhaps get to this shape with a nonlinear model or a linear model, but let's just say that this may come from a nonlinear model, the actual blue line, the truth. The fact that the tree can create more breaks and further partition your data is one of the ways that it would be able to model nonlinear relationships. Because if it adds more breaks, it's just going to create more segments of your data, right? And that way is just going to be able to model or to get close to that nonlinear relationship. Some models, if you remember on our optimum finding exercise, some models cannot model nonlinear data, right? They're just fixing their terms that they're not capable of modeling nonlinear. In this case here, this algorithm can model linear and nonlinear relationships. To me at least, one of the biggest pros of this model is that it's creating one tree, which is going to change when we talk about random forest. But just to set the stage, it's just creating a single tree that is highly interpretable, right? You have like your output is basically a tree that has decisions, a decision tree, right? You know exactly what variable you're talking about. You know exactly where the breakpoint is. You could even implement this algorithm by hand, right? I mean, it's not something like you could even create this tree, and then let's say you train this model. This is the final model that you have. You can plot it and see how it looks like. And I tell, hey, I have this new observation here. Can you make a prediction? You could potentially make a prediction just by looking at this plot. You just get your new observation, look at all of your predicted variables for that new site here that I'm just giving you. And you just see, well, okay, this observation has cumulative precipitation more than this threshold, so it goes to the right, right? You can really even make a prediction just by him. So it's a very simple model and highly interpretable, which a lot of times, and you're going to see in this class, that there is normally a trade-off between model complexity and model interpretability. Models that are really complex, they may be the best at predicting, but they also can be very difficult to interpret. It's hard to know what's going on behind the scenes because there's so many things going on. It's hard for you to know exactly and give you a really easy understanding of what's going on. With CIT is very simple, right? This is the model. You can see it. You know what it is. You know what the variables are in it. You know what are the breakpoints. Easy to interpret. So this trade-off between interpretability and complexity is something that normally people have to weigh in. Sometimes you may be training a model for somebody that really wants to know what is going on. How are you getting to that prediction? Then maybe a model that is simpler, like conditional inference tree is a simple model in the sense of machine learning, but is more interpretable, can be pretty good for that case. But if your goal is just prediction, regardless of how you get there, maybe other models can do better, like random forest or even some type of neural network can be a better model if your goal is solely prediction and you're okay with losing interpretability in those cases. So again, the trade-off between model complexity and predictive performance and interpretability, and keeping those things in mind. A lot of times you see papers where they train at least 3 models, and they start with a very simple, an intermediate complexity, and a very complex model. Because if you think about it, different models will work better or worse for different data sets. But if you test at least a few models that they range in complexity, and you can check their performance as well, maybe you can look at that trade-off for your own data and see, well, with the CIT, I'm getting a test set R square of 0.6. With a random forest, that goes up to 0.7. Maybe with a neural network, it goes up to 0.75. You can look into the metrics and then decide if you want to focus on the model that has best predictive ability, or maybe look into some trade-off between predictive ability and interpretability, if you want to optimize both of those things. All right, so another thing that's a pro of this model is that it can be used with both numerical and categorical response variables. In the case of ElasticNet, it only works with numerical variables, like ours, like strength. In this case here, we could have a categorical response variable, which we don't, but we could, and this model would be able to handle that as well. It would be a little bit different way that we would interpret it, but it would work for that. Well, some of the cons of this model is that it can have high bias. So this model here can be, it's very easy to overfit because as you saw, if you allow it to grow more, it will overfit. And so it's a model that's very prone to overfitting. We have to have that in mind and try to do our best to train it. And it has a potentially lower predictive power. Not always, but it could have a lower predictive power. And the reason for that is because, again, if you look at the final tree that it created, so if we were to go back to that first plot that we saw, any observation that matches any of these conditions, right? So let's say rain cumulative less than 387 and PAWS less than 184 millimeters. All of those data points, you see the distribution of data points on the training set is all these points, and you have 61 points there. So you see that there is variability in yield for those points. However, if you use this model for prediction, the model will predict the mean of this box plot, regardless of the variability of yield. So that is something that this model has a con, is, when we get to random forest, which I think is the next exercise, you're going to see that random forest can give you a continuous numerical prediction. It's not going to be bounded. It's not going to be binned like this is. So one of the cons of this is that although on the training set, you see variability in each one of these box plots, but if you use this model for prediction, each one of those conditions will just give you a prediction of the mean of the box plots. Basically, on the prediction, it ignores this variability that you're seeing here. So that is one of the cons of this model. All right, so we have, we're going to start here with our actual modeling now. Any questions on the theory of this model before we move on? All right, so I have 3 new packages for you to install: PartyKit, Fine-Tune, and Bonsai. Please go ahead and install them. You know the drill. Make sure you don't leave your install packages active in your script after you install it. So just to give, while you're installing that on your side, PartyKit is one of the packages that implements conditional inference trees in R. There's more than one. This is one of them. Fine-Tune is a package that's going to help us to fine-tune something about this specific model, and Bonsai as well. So Fine-Tune and Bonsai are going to help us to fine-tune specifically to this model, and you're going to see why when we get there. After you have installed it, make sure you just run the chunk to load all those packages. So Tidy Models, Tidyverse, VIP, we have used those before, and then PartyKit, Fine-Tune, and Bonsai. All right, I asked you to copy that same weather data set that we used on the previous example to this data folder. So assuming you've done that, you can just go ahead and run it, run this chunk, and you're gonna, this is the data set you're already familiar with: 698 rows, 75 columns. I'm not gonna spend too much time here because we already covered that. All right, so we're going to use a very similar workflow to what we use for ElasticNet. And I think I want to ask you to perhaps also try to notice some of the differences, but also the commonalities between them. Because again, we're using this framework from Tidy Models because it helps you to easily train new models with a otherwise very similar workflow and code. All right, as you remember, the first thing we're doing here is going to do data split and data processing as our first step. I left you the code because we have already done this before. So we're just setting seed, doing the initial split with a 70-30% proportion here, 70 on training, 30 on testing. And we're stratifying by strength just to make sure that we have a similar distribution of predicted variable across training and testing. So if you just run that, your weather split, again, has 487 rows in the training, 211 rows on the testing, and then 698 rows total, if you just put them together. Then from that initial split, we basically pull out our training data by using the training function on that previous object. And then we can really see what are those 487 rows on our training data. We go to the next chunk and do again on the test. So we retrieve those 211 rows from the test as well. And then I left you here the semicode because we already done this, but just to look into the distribution of strength across train and test. This should be the same plot as we had on the previous exercise because we set seed. So we should have the same number of rows in training and testing as the previous exercise. And because we did stratify sampling based on the predicted variable, that predicted variable has a pretty similar distribution across training and test, which is something that we want to have. All right, that's all the pre-processing, really not any difference here. As you can see, pre-processing was the same as last time. We're gonna put our test set to the side. We're not gonna touch it until the end. And we're gonna focus on our train set to do the training part of this. Or sorry, actually we have data processing. I was skipping ahead. So yeah, before we do that, we have to do data processing as well. Again, I left you here a list of potential data processing steps. Today, we're just gonna remove unimportant variables and we're gonna plug that into a recipe just like before. I left you again here this link to this table, which is what you would use to see what are the recommended pre-processing steps of this algorithm. So if we were to open that link, the model type we're using today is, let's see, decision. Yeah, is decision tree. This is the model type we're going to be using. And we see that it does not require any of these things. It does not require normalization. So we don't really have to do any of those. I still want to remove those variables that we removed that were like from the months outside of the growing season. I still want to remove them, but we're not going to have to do normalization, which is something we had to do previously with ElasticNet. So I left you the recipe. We're just setting the Y variable and the X variable by just giving all of them in this dot. And then giving the data, and then we're removing all of these variables that have the months on the column name, have the name of the months that are outside the growing season. And then I left you here the normalization step commented off because I wanted to remember that this could be a one step that is very common for us to have to do depending on the algorithm. But for this specific algorithm, we don't need that. So if you just run your recipe, we have our recipe here. Once we create those steps, they're just a list of steps, but they have not been applied yet to your data. So we're going to go ahead and apply them to your data by giving a recipe to the function prep and then assigning that to this object. This is the same as before. And now we're ready to start the training process. Notice that the entire pre-processing, except for the fact that now we did not need to use the normalization step, but everything else is exactly the same as before. And again, your recipe steps will be model dependent. In this case, we did not need to normalize as we did in the previous exercise. But up until this point, everything is pretty similar, pretty much the same except removing that normalization step. All right, now let's get into our training part of this model. So we need to first specify the type of the model that we want to train, which engine we want to use, and in this case, which mode we want to use. And I'll tell you what I mean by mode. So if you recall, ElasticNet, the one we did last class, it is a regression type of model, which what I mean by that is that your Y variable has to be continuous. That if you have a categorical Y variable, ElasticNet is not going to work. For CIT, it does handle both types, both numerical and categorical. Because of that, we're going to have to tell this model to do a regression type because our response variable is numerical. And that is what is meant by mode. We have to say the mode here is going to be a regression. If we had a categorical variable, the mode would have been classification. And I have a note about that here as well in the text. All right, so if you remember at this point, we need to determine which hyperparameters we're going to fine tune and which values we're gonna have for that fine tuning approach. So the words or the arguments that we're going to use here is tree depth. That's going to control the maximum depth of the tree. So we're going to basically allow it to grow to different depths and see which depth is going to give us the best model. The min criterion is that value of 1 minus p-value that must be exceeded in order to implement a split. So maybe if we think of p-value first and then do the 1 minus that value is easier to think. If we say, well, I only want to allow variables that have a p-value of less than 0.05 to enter the model, then your min criterion would be 1 minus 0.05. That's going to be 0.95. It's just the inverse kind of p-value. Also has the argument min n, which is the minimum number of data points in a node that are required for the node to be split further. So let's say you are training your tree and there is an internal node that has 3 variables in that internal node. If your min n is 5, that node is not allowed to split anymore. So those are the 3 that we have access to train here. We're going to focus on 2 of them, if I remember well. So we're going to do tree depth and min criterion. We'll get to that point soon here. So then we have to create a model specification that will fine tune the first 2 for us, because we're going to focus again on these first 2, the tree depth and min criterion. And if you remember, well, I guess we have not talked about this much yet, but what we mean by engine here is that, so we determine the model type, we determine the engine, and in this case, we determine the mode. The engine is just, what it means is just that even if you have a given model type, there are different packages in R that can do that same analysis. I was telling you earlier that CIT, if you use another package called rpart, that package is very similar to CIT or to partykit, which we're going to be using here. However, it uses the R² as the metric to select variables rather than the p-value. So there are some differences. The engine is basically which package you're pulling that from. So we're going to be using the partykit engine here. So this is where we're going to start coding together. Let me come to my cheat sheet here, so we can go ahead. So our CIT spec model, if you can start coding with me, you go after that specifying CIT as model comment. The function name here is going to be decision tree, coming from the parsnip package, which is part of tidy models. And at this level of the model type, we're going to be fine-tuning tree depth. So tree underscore depth is what we're going to fine-tune. And if you remember, because we want to fine-tune, we're going to place this function called tune as a placeholder to tell the training model or the training step of this process to say, hey, we want to fine-tune this. If you just came here and gave 1 value, it was not going to fine-tune, it's just going to use that value, right? So if you say 10, it's going to be 10. Give it a pipe, come after the second comment there. Here's where we're going to set the engine. So we're going to use the function set underscore engine from parsnip as well. And here in quotation marks, we're going to say partykit. So again, this is what package we want the implementation of conditional inference tree to be from. Now, one thing that's different from ElasticNet. If you remember from ElasticNet, the model type was, I think was linreg for linear regression. And then both of the hyperparameters that we were fine tuning were at this level of the model type function. For CIT, the conditional minimum criterion, which is this minimum criterion argument, is specific to this engine. Because of that, we want to tell the model to fine tune that specific hyperparameter at the set engine level instead of at the model type level, as we did with ElasticNet. So at the set engine here, it has an argument for conditional underscore min underscore criterion coming from the dials package. We're going to say equals to tune. So we have a overall model type parameter that's tree depth. So every conditional inference tree, regardless of the engine, has a tree depth or hyperparameter. So that's why it's on the decision tree level. And then in the specific case of the party kit engine or package, it has this specific hyperparameter of minimum criterion, and that's why it goes here and not on the decision tree level. This is basically where we stopped with the ElasticNet. But here again, because this type of model can handle both categorical and numerical predicted variables, we need to specify the mode. So add a pipe there, come after this last comment. We're going to say set underscore mode regression in quotation marks. So this is basically what we have to set our specifications of this model in this case. Make sure you run it so you have that available, that specification available for the steps down below. And once you print it, you're going to see that you have main arguments at the level of the model type of tree depth. We want to fine tune that. And engine specific arguments at the level of the party kit engine that we're using conditional main criterion, we're also going to tune. And then it's telling here the engine we're using is party kits. Okay, so as before, we do not see a value of tree depth in an conditional tree, we just see tune, right? That's because we want the model to fine tune that for us, or the training process to fine tune that for us. Let's see, I think we can maybe get through this next step. Okay, so let me do this. I wanted to give you a break, but there is a step in this exercise that's going to take a moment to run. So I want to get there, and while it runs, I give you a break so we can optimize time. So bear with me if you can hold a little longer for a break. Okay, so now let's begin our hyperparameter tuning. As previously, we need a few things to do the tuning. So we need the model specification, which is on this object. We need the recipe, which we have. We need a resampling strategy, which we do not have yet. We have not specified. And we need a parameter information, which we also don't have yet. So let's work on our resampling strategy here. If you remember, the resampling strategy is basically on your train set. Now you're going to use only the train set to find the best combination of hyperparameters. To do that, you have to further split your train set into training and assessment, and you can do that in different ways. We're gonna, the same that we did last time, we did a v-fold cross-validation. We're gonna do the same here with a 10 or a v-fold cross-validation where v equals to 10. So we're gonna have 10 folds. If you go ahead and you run that seed and the resampling, and you just print this object as before, we have now 10 folds, right? So we basically split the data, the whole training data into 10 parts, and each one of these folds have 9 parts training, 1 part testing, and every single fold has a different part testing, right? It always goes, whatever testing part was on the first fold, it goes back to the other 9, and one of the other 9 comes back out to the second fold, and so on. If you remember, that's how we looked into this. And if we just sample one of those splits here, so the first one, so now notice that 487 is the total number of observations on that fold, which is the total number of data in our training sets. And then this fold number 1 has 438 rows. Of those 487, 438 are on the training, 49 are on the assessment. And then it does this for all the 10 folds. All right, so let's create our CIT parameters now for us to train. So before on the previous exercise, we did not have to create this in this way, because on the previous exercise, we had all of our hyperparameters that we were fine-tuning were part of the engine. We did not have engine-specific parameters like we do today. So we have to do this step here. So if you want to start typing with me, we're gonna start with the CAT spec with, if you just run that, that's the specification of our hyperparameters. We're gonna use a function called extract underscore parameter underscore set underscore dials. If we just run this and you print CAT param, it's basically going to be extracting our hyperparameters. And then we see here that for the, I mean, it's kind of hard to read because of the way printed, but for tree depth, we already have that n param set. For our conditional mean criterion, it's missing right now. So we have, that's what we're doing here. We're setting that to actually have a set of values that it will fine tune for us. So then let's use a pipe here. We're going to call the function called update coming from recipes. We're going to call that name conditional mean criterion, which is what we do want to update. Give it an equal sign, and then call the function that has the same name, conditional underscore mean criterion. So notice that we're using the update function. We're telling what we want to update, and it happens that the function that updates that is the same name as that, but then with the parentheses. So now if you run this and you print CAT param, you're gonna see that we have an n param plus for conditional minimum criterion as well. Before we did this, this was missing. Now we do have that. So this is basically setting for the recipe, or not the recipe, but for the specification of this model, what are the ranges of hyperparameters that will be fine-tuned for each one of those hyperparameters. If we go a step further and we call this object $object, we can really see what are those, what is the range that the model is going to train for us. So for tree depth is going to test from 1 to 15. So having a tree depth from 1 layer only all the way to 15 layers. That's the default amount that it's going to train for us. And then for our, the second value here is for the conditional main criterion, is going from 0 to 1, but is doing that on a probabilistic scale, which I think is just part of the model. We don't have to really worry about that, but it is testing basically a mean criterion going from 0 to 1. So if mean criterion is 0, then 0 minus the p-value is just the p-value. If it is 1, then 1 minus the p-value is going to be the inverse of that p-value. So that's what is doing here. I know this is like one extra step that may be a little bit complex, but again, we just had to do this so we can fine-tune that engine-specific hyperparameter. We had to go this extra step here. All right, so after we go through the next chunk, I'll give you a break here, but now we're going to start our search. If you remember from the previous class, at this point, we had created a fixed grid between all combinations of some values between our two hyperparameters we had last time, which are different from the ones we have today. Today, I will not show you, we could do a grid search again, but I will not show you that. I want to show you a different way of using an iterative search algorithm. And in this case, it's called simulated annealing. I want to show you how that works on this image here. So on this example that I'm showing you here is an example that was applied to ElasticNet. So the hyperparameters on this figure are the penalty or the mixture in the penalty being on the X and Y axis. So the values of both hyperparameters are on the X and Y axis. And then each panel is one iteration. Before, if you just think of the first iteration, we had a fixed grid with a lot of points. That's what we did. Now we do not have a fixed grid. The way that this algorithm, simulated annealing, works is it starts off with one combination of each one of the two hyperparameters. It trains all your folds on that combination, assesses the fit metrics, and then it considers this ring of potential next combinations around it, and that's why it's simulated annealing. So it simulates the next levels that it could incorporate, that it could run as a new combination of hyperparameters, and then it goes in the direction that has the best fit. So let's say it would be using R square as the fit metric. So the next step was the second point here. So it kind of advanced to that second point. It creates again a ring of possibilities around it. It tests those possibilities, finds the one that increases the fit metric further, and keeps navigating that way. So it's kind of like a blind search. We're allowing it to be assessing just combinations around the current combination, and then just selecting the best one, going to that direction. As you can see, so iteration 2, 3, 4, 5, and 6. So on the 6, at least in this case, it stopped right there. So that combination of on the x-axis penalty and on the y-axis mixture is what then optimized this model. There are different ways for us to stop the search. One of them is perhaps to set what is the total number of iterations you wanted to do. We're going to set it to 50, I think, but it could be higher. It could be 100. I think I would do at least 100, but in class, because of time, I'm doing just 50 to show you. But basically, it's just doing this blind search that only sees potential combinations around where it is, chooses the one that improves model and goes that direction, and then updates the region, searches for a new radius, and keeps moving blindly that way, walking through the hyperparameter space that way. I have some of that explanation here in text if you want to read, but that's basically what I just said. All right, so we're gonna now implement this in this next chunk, and then this is gonna take maybe a moment to run, and then we can take a break while it runs. So if you come here on the CAT grid results, this is gonna be the result of our search. Let's give it, this is where we gave that tune fixed grid or something like that last time. This case, we're going to use a function called tune sim anneal, so simulated annealing. I'm going to break line just to make it more readable. It has an argument called object. This is basically our specification, which is the CAT underscore spec. If you just run that, this has the specification of the model, the engine, the mode, and all those things. It has an argument for preprocessor. This is where we give the recipe. So we call this weather underscore recipe. So it's pre-processing our data using the recipe. We need to give the resampling strategy. So it has an argument for resamples that we give our resampling object called resampling fold CV. In this case, again, because in this model, we have engine specific hyperparameters, we have to tell it about that. So it has an argument for param info that we give the CAT underscore param object that we created above to update that any specific hyperparameter. And then finally, it has an argument for iter, for the number of iterations we want to do. I want to do this as 50. Again, I would recommend you do as 100. If you're doing for a research, at least 100. Here we're doing 50 just for time constraints. So if you go ahead and run this chunk, that is probably going to take a moment. And then I'll give you a break. So 10:44. I know we're going just to 11, but I also want to allow you to take especially a restroom break if you're needing. So let me give you 5 minutes here, and then we'll come back. All right, our timer is up, so let's keep moving. If you're online, please make sure to open your cameras. So maybe if you did take a break, maybe you were not here when this happened, but basically it was showing us this log here as it was moving through the search. So it is optimizing our MSC. The initial best value of our MSC was 3.004. And then at each at each iteration of this algorithm, it is looking for it's creating that simulated annealing and then identifying the potential new combinations of hyperparameter values, evaluating them, and giving a new RMSE. As you see here, for the first through the fourth iteration, it found a suboptimal or it found combinations of hyperparameters that created suboptimal solutions, meaning that the one it started with was still the best. On the fifth iteration, it found a better solution. So we found a combination that was the new best that lowered the RMSE compared to the starting point. And then it just kept moving in that direction. So accept so there's some ranges of values of what it considered a suboptimal. And what is a better suboptimal? I don't remember what these really, like, what are those thresholds, but basically a suboptimal would be a combination of hyperparameters that produces an RMSE that is lower than the current, but is still keeping that in mind. And better suboptimal is the same. If it gets stuck in not finding new position or new values for a given number of iterations, then it goes back and restarts from the previous best. That's basically what it's doing. So it walked this space all the way here, did not find a better solution. It returned to this combination here and restarted again to see if maybe it would find another route starting from that best. On my log, if I think I see a new best on iteration 5. And I don't think it was able to find a better solution than what it found at iteration 5, at least on my side. If you were to have run this for 100 iterations, maybe would have had more chance of finding a better optimum for you. And maybe we would have a new best that was not just the one that it found on iteration 5. So that's basically what it's doing, is walking that hyperparameter space and trying to find a better solution than what either started or one of the ones that you found in the middle. Yes, John.
If it splits to minimize error on both sides, then how could it restart and find a better?
So, okay, so I think your question perhaps goes back to the way it's splitting the tree, right? Or the splitting a variable in the tree. So what's going on here is that for each one of your folds, it's running a lot. I mean, it's running this new combination of hyperparameters across all of your folds, and then assessing the overall RMSE. So this is separate from the splitting the HEPs in a given tree, right? This is across all the 10 folds. Yeah, so this is not, well, the variable split in the tree is happening, but it's not using that to determine the better RMSE, right? It's looking at, so imagine you have 10 trees for this specific combination of hyperparameter values. It creates those 10 trees on one on each fold, and then across all those folds, look at what is the RMSE on the assessment set. And this is that mean RMSE that you see right there.
Dr. Bestos.
Yes.
So for the output, I'm getting the optimal, like the new best at 13th iteration. Unlike yours, you got on 5th iteration. So I'm wondering, even after setting seed, if there's any random component, like why is it mine different than yours?
Interesting. Yeah, I don't know, because we did set seed. I'm not sure exactly why it gave a different iteration. We can, so the next step is going to be to check what was the combination that gave the best, and then at that point maybe we can compare and see, because it may have reached the same conclusion even though it got there differently.
The other thing is that even though 13 is the new best for me, the RMCE is the same value as yours.
Okay, yeah, so maybe you just got there, but it took a few different steps. But it's interesting, did anybody get new best at 5? Huh, okay.
I just plug in.
Okay, yeah, I'm not sure what's going on, but yeah, even though we set seed, I mean, all of this has a lot of randomness to it, right? Just selecting or creating the anneal around or simulating the anneal around the current value. I mean, the radius is fixed, but which values are considered within the anneal may be a little bit different, and maybe that's why it's going a little bit different routes. I mean, we did set seed at the fold as well, right? But as you can see, there's a lot of randomness in the process. We're trying to minimize the effect of that so it is reproducible, but as we're seeing, it's not fully, you're not fully finding what I'm finding, but. All right, I guess I just want to show you here. So if you go back to this, so do not run the whole chunk again because we don't have the time. But if we just call the object name, so CAT grid results, and then we go inside a column called metrics. I want to pull just the second one here, which is going to be the second iteration. So if you just pull that, basically at that iteration, it was evaluating a tree depth of 10 and a mean conditional criterion of 0.9926. Remember that the p-value is just 1 minus this, so it was a 0.001 p-value or something like that. And at this evaluation of this combination of hyperparameter values, it had an RMSE of 3.41 and an R-square of 0.05. Right, so and then you have that for each one of the iterations, which are evaluating a different value of both tree depth and conditional mean criterion. All right, so I want to collect fit metrics across all the folds and for each iteration and make a plot. I'm not going to walk you through the plot. You're welcome to play around on your side. But if you just run this plot, we're basically going to see this, which we have conditional mean criterion on the x-axis, tree depth on the y-axis, and the numbers that you see in the plot are the iteration number. So you see how it was walking the space here. And then the color is just the factor of the mean of the RMSE. So basically, if you look, we want the lowest RMSE, which was 3.003, so it's the dark blue, which happened somewhere around here. It's kind of hard to tell what was the iteration specifically, just because there are so many that were together. But you see how it was walking the parameter space, right? The iterations 0 was on the top here, and then it was walking towards this side. So the gradient of better model fit was bringing it to the right side of this plot. If you had increased, so something cool also to notice is whenever it keeps going a direction, but it's not improving model, it comes back to the new best. We can see that here, maybe you see like 43 is here, 44 is here, 45 is there, and then it's really not changing or not changing significantly the RMSE. So it just returns again to the best, to the latest best, which I think is this one here. Yeah, I think, okay, so your plots look different. I think it's probably because of how you got the different path. But I guess, were you still able to get your best around this region? Like if you look at, I know it's the best because we won the lowest, and the color, this dark purple for me is showing up around here. I think you may have. But like, is your dark purple around this region? But I mean, if you just look at the dark purple, even though the path is different, but is the dark purple around here?
Yeah.
So we found the same solution. Okay, not for I-10, seems like.
Yeah, Dr. Bestos.
Okay. Yeah. Yes.
Yeah, so for my case, the points are so overlapped that I cannot see the dark purple or any color. Like all the numbers are right on the point of the dots.
Okay, so
So
let's do this. I mean, this is just a visual assessment that I want you to be able to see how we use the perimeter space. Maybe we should really judge that by pulling out that model and really seeing what was the combination of conditional mean criterion and tree depth that optimize it. So let's do that. Well, I guess before we do that, just to show you, this was using our MSC, which we want to minimize. But then, let's see here. Shakir's, I'm gonna mute you here. But so if we look at the same plot, but now, oops, looking at R square instead, so the metric being R square, if you just run that, well, you may be seeing something different, but in this case, we want to increase, we want a higher value, right? So in this case, I would imagine that your yellow in this case is the highest to be potentially close to where my yellow is, even though your path is different. Now, okay, so it's already 11. Let me see. Yeah, we still have some chunks. Maybe we can stop here because I don't want to go too much later. And then we can continue this next class. We're going to basically continue and finish this next class and then start a new exercise, which I think is going to be random forest in the next class. But yeah, so let's stop here. Let me open a attendance issue on our GitHub. All right, I just opened the attendance issue, so please make sure to claim your attendance and then you're dismissed. I'm going to stick around in case anyone want to have some questions, or maybe if somebody can show me your path as well. I'm interested to see, how that differed. But otherwise, I'll see you on Thursday, and then we'll finish this exercise and start a new one as well. All right, thanks everyone.